Well, good morning, class. This will be the video lecture for section 3.4, non-uniform torsion. First of all, in section 3.3 that we covered earlier in the week, we covered uniform torsion and the formulas for displacement. So if you just recall, we had an angle of twist called phi, which had the formula of T, which is torque, times the length of the bar, divided by G, the modulus of elasticity and torsion, and IP is the polar moment of inertia. Anyway, that's the angle of twist, and the units are in radians. There's an occasion where we will need to know the rate of twist, and so the rate of twist is T over GI, and the units there would be radians per unit length. The most useful thing that we found was the torsion formula for stress, and that is that tau is equal to TR over IP. We found that the maximum torsional stress occurs at the outside of a circular tube or circular bar. The units there are newtons per meter squared, or PSI. The polar moment of inertia was looked at, and we found that for a solid bar it is pi d4 over 32, and for a tube, pi over 32 times the differences to the fourth of the tubes. Now, for non-uniform torsion, we're going to have three cases that we're going to discuss, actually just two. We're going to talk about two cases, and the first one is that we have prismatic bars, prismatic segments of bars, and we have uniform torsion in each segment. And so the phi, or the change in angle, the angle of twist, is the sum of whatever happens in each of the individual segments. So whatever happens in segment 1 plus segment 2, and the total will be the total angular displacement. All right, so let's look at this problem. This is 3.4-1, very first one. So here's a bar that's under, it's a fixed support on that side. It's got a couple of torsional elements here. This one is 20,000 going in that way. This is 8,000 going in this way. The bar is 30 inches long from here and 20 inches long from here to here. So we can see that the torque is uniform between AB and BC. So there's nothing changing the torque, so that's going to have uniform torque or uniform torsion between here and here, and it'll be uniform between here and here. It's not going to be the same, but they are going to be uniform there. And so because it's uniform, the formula phi equals TL over GI applies to each section. All right, so let's define what is positive. Positive torque and phi occur together. So in other words, a positive torque causes a positive phi. Now positive is defined by the right-hand rule. And so you can see my little curly Q here, my little torsion sign. If it's going in this direction, which is clockwise as you're looking at the bar on this end, then it causes a torque in this direction. So that's by the right-hand rule. If you remember from statics or other things, if you go this way, then you got the thumbs going straight out, and so that this being a torque in that direction that yields a positive thumb, if you will, in that direction. So by virtue of the fact that this is clockwise as you're looking, counterclockwise as you're looking at it, that means that that is a positive torque. And if it's positive torque, then it has to be on this end, then it's obviously positive on that end. If you were to look at this end straight on from the other side, you'd see that it would be a torque going that way and the thumb would be going straight out. So it's got to be positive at both ends of the segment because the segment is in equilibrium. All right, so then let's go back to the drawing, and we can see that this one, because it's going this way, this one's going to be a positive torque, and this one's going to be a negative torque. We can sum torques, because the bar is in equilibrium, we can sum all the torques equal to 0, so we're going to say that the reaction at A, let me go back up to this, and we're going to draw a little reaction here, and we're going to say the reaction at A has got to be the, plus these are got to all be equal, so I got RA minus T1, T1 being the negative torque up here, plus T2 is equal to 0, and I find that RA is equal to 12,000. Now we may use that, we may not. It's kind of nice to know if we're going to solve some problems, but in this case, let's just define what the angular displacements are, the phis. So let's look at the first segment up here, BC. because it is a positive torque, we already defined that, we can know that this equation applies, phi BC, so TL over GI. It's a positive torque means it has a positive phi. So going that way, I'm looking at it from this end. I actually don't even have to worry about that end because whatever it is, it's in equilibrium. All we really have to know is one end of the bar. And in this case, if I do that, I put 8,000 psi times 20 inches long. G is 11 e to the 6 according to the problem. The diameter on this end of the bar is 1.75 inches. Putting the formula together, I get 0.158 radians of torque, of angular twist in this segment. All right, so now let's go to segment AB. Back up here. Again, this has got a negative torque on that end. But if we're going to draw a little method of sections right here, if we're going to draw a little method of sections here, we have to consider both this one and this one. So let's look at the end of the bar. So it's got 20,000 going that way plus 8,000 going that way. The net is going to be 12,000. 20,000 that way, 12,000 that way. That means the net is going 12,000 in. So that means this one has a negative torque, obviously a negative phi. So I can add those up. I get a negative phi. I can find out the displacement, minus 12,000 times the length of 30. It has a different diameter down here, 2.25 inches in diameter, and I get a negative phi of 0.013 radians. I add those together and I get that the total phi is 0.00279 equals 0.160 degrees. And it is a positive number. That means that it has a total positive angle. If it has a total positive angle, that means it is twisting just a little bit in that direction. All right. The next piece of the problem is what is and where is the maximum stress? Well, the stress was given as tau is equal to TR over I, but we don't know in which segment tau max occurs, so we're going to have to evaluate both. Now for tau, stress is stress. We have negative stress and positive stress, but if we're trying to find out what the maximum is, we don't really care if it's positive or negative. So I'm saying the signs don't matter in this case. So let's do the tau of AB. AB, again, the big section, 12,000 was our net torque that we decided. The radius is the diameter over 2, and then we have pi over 32 times d to the 4th. That's the polar moment of inertia, and I get the stress in section AB is 6,557. I do the same thing for BC, and I get it as 7602. The difference here is it's got a different stress, a different torque, and a different diameter. So it will have a different stress, and you can see that this is bigger, so the maximum stress occurs in BC, the smaller little section. Anyway, so that's how you approach them. We will let's just get a little more practice in doing torques and trying to figure them out. Here we have a tube that's got, this is problem 3-3.4-5. Here's a single tube, but it's got lots of different torques. This is like a gear shaft, or perhaps, and it's got driving different things at different, and there may be some different resistances based on the things that it's driving. So anyway, so we've got several different torques here, and we're just going to get some practice on positive and negative torque. Remember, for any section, if you're looking at it from this side, positive is coming out, or negative would be going in, depending on what the direction there is. So let's look at section AB. We'll start on that end this time. We can see that this has got a torque in that direction. So if I were to put my right hand rule again, put my thumbs going this way, or my fingers going this way, the thumb going that way, I can see that the torque is going in. So I drew my little arrow like that. The torque's going into the section. That means that it is a negative torque. So it's easy to see by the right hand rule, this one is negative. All right, let's move on to section BC here. In this case, we have to add those two together. So I got one going that way, one going that way, 1,000 going that way, 500 going that way. So my net is 1,000 minus 500, so my net is still negative, has 500 pointing in, which means that it's still a negative torque, means it has a negative phi. the segment is in equilibrium. We only really have to evaluate one end. I'm not bothering on the other end because I know that whatever I find over here, if I can find it definitively, I know that the other end has to be equal to it because it's not moving. All right, let's do the next one. This section right here. So I have to add that one and that one and that one. So I need to say negative 1,000, positive 500, negative 800. So again, negative 8,000, positive 500, negative 800. So I get a net of negative 1,300 in this section right there. All right. So again, another negative. And then the following, and the last one, that's the easiest because either one of the ends is easy because you know, if you know what the end is, you know what the whole segment is. And so in this case, I'm not even going to look at that, and I'm going to look at this end. So in this case, I got a 800 going in that way. I know that it's pointing in because of the right-hand rule. That's negative, so again, they're negative. So all four segments are negative, and if we were to add up the fees for each one, then we would obviously get a negative fee. All right, so I'll tell you what, let's pick some values and see if we can solve for a fee. So let's just say that each segment is 12 inches long. We have an I, it's uniform along the whole tube, is 0.07 inches to the fourth. Let's say that it's got a G of 9.5, so it's pretty stout. It's probably steel or something like that. And we could figure out what the total fee is by just saying TL over GI for each segment. A G and I, since it's a bar, are going to be the same for each of the segments. The torque is going to be different for each segment, and I'm saying each segment is also 12 inches long, so it'd be pretty easy to do my arithmetic. So minus 1,000 times 12, minus 500 times 12, minus 1,300, and we get 0.65 radians or 3.72 degrees. That would be the total twist from the beginning to the end. Now, we don't really have a fixed reference point, so all I'm just saying is one end may be going this way, but the total twist will be 3.72 degrees from beginning to end. Does that make sense? I hope. All right, and then the problem that was in the book is where is the tau max? Well, tau max occurs someplace in that bar, and we don't really know where, but we do know that it has to occur where the maximum torque is. So if we go back to which segment had the most torque, well, it was in this segment right here. And that was, in that segment, we had negative 1,300 in that segment. So that meant that that's where the maximum stress will occur. So let's just find out what that stress is. So the stress is tau is equal to TR over I. And we're going to say that it occurs at the outside of the bar. The outside of the bar is, the radius is, the bar was 1 inch, and so the outside of the bar is going to be 0.5. In the book, the question is where, it's actually a tube, and we're trying to find the inside diameter of the tube such that the outside, or so that the maximum stress is limited to 12,000. So I'm going to set the equation up here. Tau is equal to TR over I. Put my I over here, my tau there, and I'll say that torque is 1,300. The radius is 0.5 divided by my maximum stress of 12,000. Now my IP is equal to pi over 32 times d outside to the fourth minus d inside to the fourth. And this is what I want to solve for, is the inside diameter such that with that torque and that maximum stress, everything balances out. So anyway, just solve this for d inside, and I get the d inside is equal to 0.81824 inches. All right. All right, I'm going to stop the video now and start it up again in a second.